Assalamualaikum warahmatullahi wabarakatuh. So we are from group 2. We present Primality testing for Frobenius method. So this is our group member. First we have Muhammad Anas Abumi bin Muhammad Hidayat. Second is me, Muhammad Azlan Naim bin Hani. Third, Muhammad Uwais Korni bin Jeffrey Jamsari. Fourth, Muhammad Hafiz Sahmi bin Mazlan. And lastly is Ahmad Zulkarnain bin Muhammad Zuki. Okay, for the early development, used for cryptography, number theory, and computational mathematics. Rely on deeper algebraic concepts like Frobenius automorphism. Gained popularity for its efficiency and strong theoretical foundation in modular arithmetic. For the modern user, it is often used in a scenario requiring high confidence in family without exhaustive computational effort.
Okay, for now, we move to the theories. It does not have a single fixed formula. The principle is a candidate number n is checked by examining its behavior under certain modular equations derived from Frobenius automorphism. Second, the test verifies congruence modulo and other conditions that composite number fail to satisfy. And lastly, the Frobenius Primality test often involve properties of polynomial roots over finite fields, ensuring that specific algebraic forms hold if n is prime. Okay, for the advantage and limitation. For the advantage is high confidence, improved accuracy, and algebraic depth. It's a very robust encryption. And next, we move to the limitation. For the limitation is complexity. It need for algebraic computations and modular arithmetic in higher degree fields. Next is lower in practice, slower than ASP or other modern algorithms for very large numbers. And lastly, its specialized usage, primarily suited for specified applications rather than general purpose primality testing.
And I will be presenting a efficiency analysis. Okay, there is 3 points that we can get. Is firstly, time complexity. The complexity depends on modular explanation and operation at algebraic field. Click O log to the power of 3n to O log to the power of n for numbers of size n. Practicality, efficient when combined with other tests like Miller-Rabin to balance speed and confidence. And lastly, comparison, faster than exhaustive trial division, but less practical than probabilistic method like Miller-Rabin or routine large number testing. Next, we can go to the coding. Okay. This slide shows a Python implementation of the Frobenius primality test, supported by function for number, by function for number theory operation like GCD and the Legendre symbol. Left side, supportive function, GCD A, B, calculate the greatest common divisor, helping find co-prime numbers, Legendre symbol A, N, determine if a number is a quadratic residue modulo N before validating the discriminant in the Frobenius test. The Frobenius test functions start with basic check, ruling out numbers less or equal to 1, small prime, and even number greater than 2. To the right side, Frobenius test logic. Okay, the test select a discriminant delta equal to 5 and check if it's a non-square modulo n using the Legendre symbol. It then find a value a for prime to n and compute x squared equal to a to the power of 2 minus delta percentage n to check polynomial condition. If all condition pass, the numbers is prime, otherwise it composite. For example, we can see that the example test number equal to 37 which return prime. Okay, this implementation demonstrates the Frobenius test but can be optimized by dynamically selecting discriminant.
Now let's take a look at example 1. Number 1, choose a quadratic polynomial. To select a quadratic polynomial, fs equal to x squared minus bx plus c such that the discriminant delta equal to b squared minus bc is not a perfect square modulo n. The common choice is fs equal to x squared minus x minus 1 with delta equal to 5 because 5 is not a perfect square modulo most primes. Number 2, check quadratic residue. Verify if delta equal to 5 is a quadratic residue modulo n equal to 37 using a legendary symbol. 5 over 37 equal to 5 the power of 37 minus 1 over 2 mod 37. Calculate, we got 5 to the power of 18 modulo 37 equal to 1. Thus delta equal to 5 is a quadratic residue modulo 37. This indicates the polynomial fs equal to x squared minus x minus 1 is suitable for further tests. Now let's take a look at example 2. Number 3, modulo congruence check. Next, the test polynomial fs modulo 37 for specific x. For fx equal to x squared minus x minus 1, check if f a the power of n equal to fa modulo n. Let a equal to 2, f times 2 equal to 2 the power of 2 minus 1 equal to 1. Calculate f times 2 the power of n modulo 37. F times 2 the power of 37 equal to 1 the power of 37 equal to 1 modulo 37. This satisfies the congruence condition. Since all conditions are satisfied, n equal to 37 is surely a prime number.
Next, we have arrived to the conclusion. In conclusion, the Frobenius primality test is a rigorous and advanced method for determining whether a number is prime or not. Due to its complexity and intensiveness, it managed to win and lose at the same time, which is pros and cons. On the winning side, it is very robust and cannot easily be hacked, but on the other side, it is slower than other methods because of the same complexity. Lastly, our lecturer once said, cryptography is all about efficiency. Thank you for your attention.